So now let's see if we can generalize this to answer more complicated queries. So one thing that you can notice about this formula is that this number O of square root r is just the crossing number, right? This is the crossing number because this is the number of the triangles intersected by the line that is the boundary of your half plane. We just plug this directly from the crossing number or from the partition theorem. So now let's say we want to answer a slightly more complicated queries. We want to answer triangle queries, where every query is a triangle. We build the exact same partition tree, exactly the same, so nothing changes over here. And here the query that we have is a triangle. So for example, in this particular case, the triangle could be like this. Interestingly, our query algorithm is still the same. We look at every partition. So let's say you look at the green partition. It is enclosed in a green triangle. If it's completely inside, we add it to the total. If it's completely outside, we ignore it. If it intersects the boundary, we recurse in it. So for example, in this picture, you recurse in all of these triangles. Okay. So what is the recursive formula for the query term? It turns out, just ironically, that it's exactly the same query. It's the same formula. So what just happened? Why is it the same? It is because we have, first of all, an O notation here. And second of all, this value here is the crossing number, right? If you remember. And here's the thing. The crossing number of a triangle is 3 times the crossing number of a line. Because a triangle can be decomposed or is contained inside 3 lines that form its boundary. Okay. So you look at all these 3 lines that form the boundary of this triangle. The number of partitions that are intersected by the triangle cannot be more than the sum of the partitions intersected by these 3 lines. Each line intersects O of r partitions. So in total, you intersect 3 times O of r partitions. And since 3 is a constant, you can just put it inside the O notation. So you intersect O of r subproblems. So essentially, you get the exact same query and you get the exact same answer. Okay. And here we can tie it to the concept of canonical sets that we looked at in the lectures related to orthogonal problems. Here we can also use the concept of a canonical set. Go back to the, let's say, the partition tree, right? So we have a partition tree. For every internal node, look at the subset contained in it. That's a canonical set. Or if you want to think of it as a partition, or if you think of it in terms of partition, you start with a canonical set, P, you partition it into R subset using the partition theorem. Each subset is a canonical set, and then you recurse on each partition. Okay. So by this definition of a canonical set, we can show that the set of points inside any triangle is a disjoint union of roughly square root n canonical sets. How do we get that? By just simulating the query algorithm. Remember the query algorithm, if you had a partition that was outside, we ignore it, so that doesn't count. If it's inside, I would normally add the total number of points inside this to the total that I have. Now instead I just add this subset or this canonical set to the list of canonical sets that forms the disjoint union of the canonical set inside the query triangle. Since the set of points that are contained inside the triangles that I use for partitioning are disjoint, it follows that the canonical subset that I pick will form a disjoint union of the set of points inside this triangle. Okay. So this is true, and it actually shows you a very powerful property, because now it follows that we could answer any complicated query. For example, if you want to list the number of points inside the query rectangle, you do the same thing. Now your canonical sets are defined using this partition tree, so you can output the elements of every canonical set in essentially O of k time, where k is the output size. If the points have weights and you want to find the maximum weight, for every canonical set you can store the maximum weight, and then you only need to look at this roughly square root n maximum weights to find their maximum to return as a maximum weight contained in the query, and so on. So essentially, any query that we could answer using this canonical set property, we can answer it using this problem as well. One funny thing here is that the KD tree is essentially a special case of this type of partition tree. In the KD tree problem, we had square root n as the crossing number of the KD tree, which is kind of the same that we have here, except that here the queries are much more general. So there's lots of common themes between these ideas and the ideas that we looked at in the orthogonal problems.